Right. Our next topic is CO2 laser. So I've seen different types of lasers: solid state lasers, gaseous lasers like ruby laser, helium neon laser, semiconductor laser, and all. So here CO2 laser is also another gas laser. So just like helium neon laser, here we'll be using helium, nitrogen and CO2, three gaseous mixtures. Right, so our next topic is CO2 laser. So already we have seen about some solid state lasers and gas lasers like ruby laser, helium neon laser and semiconductor laser. So this is also one of that gas lasers. So this can be operated in both continuous mode and pulse mode. So here we have helium gas, nitrogen gas and carbon dioxide gas in the ratios 10:1:1. So just like in helium neon laser, here also nitrogen takes the electrical energy and gets excited, and then so here just like in helium neon laser, nitrogen takes the electrical energy for excitation and it will be transferred to carbon dioxide, and helium acts as a buffer. Helium acts as a buffer agent, to maintain proper pressure in the chamber so that more number of collisions will take place and atoms will go to ground state quickly. So for that purpose helium will be used. Nitrogen is to take the electrical energy and get excited. CO2, the energy will be transferred through collision. To understand about the energy levels of carbon dioxide molecule, so here the majority is the vibrational energy levels. So the one that falls in the visible and near infrared region is vibrational modes. Vibrational energy levels fall in the near infrared region. Okay. So carbon dioxide molecule is a linear molecule. So three atoms connected in a linear format. So here you have so the degrees of freedom. How many degrees of freedom for this molecule? So here you have three atoms with 3 degrees of freedom. Each atom is able to move in 3 directions. So you will have 3n degrees of freedom. Nine degrees of freedom. Out of this, as a molecule as a whole, it will have only 3 degrees of freedom. So each atom has here each atom has 3 degrees of freedom, and as a molecule as a whole it will have 3 degrees of freedom. So translation modes. Three translation degrees of freedom along XYZ directions for the molecule, and 2 rotational modes. So rotation along the axis has no effect. Since it is a linear molecule, rotation along the axis has no effect. For linear molecule, rotation along the axis is negligible. So these 5, if you remove these 5, number of vibrational modes are 4. So total 9, 3 are translational, 2 are rotational, remaining 4 are vibrational degrees of freedom. So this linear molecule can be vibrated in 3 different modes. One is symmetric. So here you have 4 vibration modes. So 4 vibration degrees of freedom. So one is symmetric. So the central atom remains stationary and the other 2 atoms will be vibrating symmetrically opposite to each other. Another is vibration mode, where central atom may be moving in one direction and the other 2 atoms will be moving in opposite direction. So this is first vibration mode. So if the central atom moves in one direction, other 2 atoms move in other direction, you have bending. And this bending can have another mode also. Like if both are perpendicular to each other or not perpendicular to each other, both will be considered as second vibration mode. Both are bending modes. And the third one is asymmetric vibrations. So here the central atom and one of the atoms will move in one direction and the other atom will move in another direction. So this is third mode of vibration. So out of 4 degrees of freedom, we have 3 different modes of vibration. One is symmetric vibration, another is bending, third one is asymmetric vibration. So if you see the energy level diagram for these 3 modes, bending is little easier out of these 3 activities. So if I consider 0, 0, 0 as the ground state, so these are the 3 vibration modes. I am considering all of them as 3 different digits. So this is nu1, nu2, nu3. So out of these 3, bending is little easier. So 0, 1, 0 is the first excited state. So nu2 mode excites first. So next one is 1, 0, 0. Symmetric mode. Next one is 0 2 0. Here it is 0 0 1. Antisymmetric vibration is most difficult. It takes larger amount of energy. So this is the energy level diagram for vibrational modes of carbon dioxide molecule. So this is the photos. So 0 to 0 is even lower than 100. And this nitrogen energy levels are here. So for nitrogen 0 0 0 is here. Another one. So first excited state for nitrogen atom is here. So the difference of the energy will be transferred through collision. And from here you will have two laser transitions. One is 10.6 micrometers, another is 9.6 micrometers. So more the energy gap, you will have less wavelength. So here the notation is these are symmetric modes, these are bending modes, and this is asymmetric modes. So coming to the construction part, you will have gas chamber. So you will be applying electric field. And so this mixture of gases will be passed perpendicular to the electric field. So there will be circulating like this. And here we have mirrors. High pressure mixture of CO2 and 2H2 is passed through the chamber through a nozzle. So the gases expand and temperature falls down. system has to operate at low temperatures, so that we'll have more number of atoms available in the ground state. So that means only electric field is the only excitation. I mean, to ensure that we are maintaining low temperatures. So next, NT absorbs electrical energy and passes on to CO2 through collision. సో ఎలక్ట్రికల్ ఎనర్జీని నైట్రోజన్ గ్యాస్ అబ్జర్వ్ చేసుకుంటుంది, CO2కి త్రూ కొలిజన్ ట్రాన్స్ఫర్ చేస్తుంది. Two laser transitions takes place. One is 0012 100 at 10.6 micrometers. Another is 0012 020 at 9.6 micrometers. So in this process, CO2 may get converted to CO. CO2 may get converted to CO. So to get back to CO2, water vapor is introduced. So to get back to CO2, water vapor is also introduced, and entire gaseous mixture is circulating. So we'll be replacing it time to time, but in the chamber, to avoid that CO combinations, we'll be using water vapor. So entire gaseous mixture is recycled. So helium acts as a buffer to maintain proper pressure, so that the atoms reaching to the lower laser level will come back to ground state through collision with helium. Finally, after collision with helium atoms, CO2 atoms come to ground state. And out of these two, 10.6 is selected by proper separation of mirrors. So the separation between the two mirrors of the laser cavity is some multiple of n lambda by 2. Here lambda is 10.6. So only those waves will be constructively superimposed. So with that, this is the basic principle, construction and working of helium neon laser. Sorry, CO2 laser. So here you see this ones. So when you have this carbon dioxide molecule and you are supplying energy, so when the energy is in visible region, it will induce electronic transitions. So the energy is sufficient for electron to move from one energy level to another energy level. So that is electronic transition. So if the energy is a little lower, so when you go from visible region to infrared region, lower energy, so the energy is not sufficient for electronic transitions. It will induce vibration transitions. So this infrared and near infrared, far infrared, all these transitions are in vibrational modes. So the energy supplied will be utilized for vibrating the molecule. And rotation is even easier task. Instead of vibrating a molecule, if you rotate it, it is even easier. That comes under microwave region. So it takes 100 micrometers. So what is this 10.6 micrometers? If you consider it is in angstroms, it is 10,600 angstroms. Micrometer is 10 power minus 6, angstroms is 10 power minus 10. So they add 4 more zeros. It is 10,600 angstroms. So it is a far infrared region. 7,000 is visible red. Beyond that is infrared. Sorry, near infrared region. So these are the vibrational energy levels. So we are supplying energy to. Why don't we supply energy directly to carbon dioxide? మనం కార్బన్ డైఆక్సైడ్ని టార్గెట్ చేయొచ్చు కదా డైరెక్ట్గా, ఎందుకు చేయట్లేదంటే హీలియం నియాన్లో కూడా అలాగే జరుగుతుంది. డైరెక్ట్గా నియాన్ ఎగ్జైట్ చేసేయచ్చు కదా, మధ్యలో హీలియంతో పని ఏంటి? సో ఇఫ్ యూ సప్లై ఎనర్జీ డైరెక్ట్లీ, ఇఫ్ యూ సప్లై సూటబుల్ ఎనర్జీ ఫర్ కార్బన్ డైఆక్సైడ్, what happens? All carbon dioxide atoms will be excited in one shot and they will never come back to combustion because you have continuous supply of electric field. So all atoms will be in excited state forever. You will never have a laser action. So we are taking this nitrogen as a buffer. So whenever this nitrogen goes and hits the carbon dioxide molecule, then only it will be excited. There will be some time lag. There will be some gap. So first of all, nitrogen has to take the energy, and whenever it comes across carbon dioxide molecule, then only energy will be transferred. So only batches of carbon dioxide molecules will be excited. So some are in an excited state, some may be already, some may be in the ground state. So we will have continuous laser action possible. Otherwise, we will never have a laser activity. Either we just switch on the electric field and turn off, then you may have laser action, one pulse of laser. If you directly target carbon dioxide. So that is and these helium atoms, they bring back the carbon dioxide to ground state. That is also through collision. So they are more in number, just to ensure that de-excitation process quick. So we have 1:1 ratio of carbon dioxide and nitrogen, whereas 10 times more helium. So we are primarily focusing on de-excitation process. So if the atoms remain here forever, whatever laser light will be absorbed back. Reverse absorption will take place. So you'll never have laser light. So our primary focus is on de-excitation. Okay, so once these atoms come here, molecules come to this vibration level, they will quickly come back to ground state. Because there is a 10 times more possibility for de-excitation than excitation. Okay.